And let me start to talk about it. I'll give you some more time to work on the second one. All right. Remember, when you're looking, you can see just by these three examples, I included all the kind of challenging things, right? The leading coefficient other than 1. Here, it's a special pattern, and then here, it's the difference of Q special pattern. Okay, so when you're looking at this, you have, first of all, you do have two prime numbers as your leading coefficient, or your leading coefficient and your constant. So trial and error probably going to be a doable process. However, which of these maybe looks easiest to factor? The numerator or denominator? Probably denominator, right? It fits a pattern. Okay, just kind of like what I showed on that other one. Do the easiest one for you, and it might be different for each of you, but that way it may give you a sense of what the other factors are going to have to be for trial and error. So if we start with our denominator here, what two bases are being squared? We have the difference of two perfect squares. What base is being squared here? 5x, and here 3. So when we factor this, we get the sum of these terms. So it's the same two terms. The sum of the terms times the difference of those same terms. Okay, so here's our factors, which means now when we look at this numerator, again, we're probably going to have either a 5x plus 3 or a 5x minus 3. So this reduces, again, it's not a guarantee, but for the most part, you're probably going to be canceling factors in every single one of these problems. So let's test and see what would happen. We only would need the trial and error for, I'm going to test the -3 just because I can write over the top of it and turn it into a +3 much easier than erasing. So if my first term is a 5x for this factor, what would my first term have to be here for this FOIL to work? So this is going to be x. And then my last term would have to be a -1, right? So that our product is +3. Okay, so let's look at this. If we take our outer plus inner products, 5x times a -1 is -5x, -3 times x is -3x. Is -5x plus a -3x equal to -8x? Yeah, so we found it. Again, there's other rules you could use to test this. If you know that the sum of the terms is negative, the product is positive, meaning the same sign, they'd have to be negative. So there's some other things you can do for this, but just using trial and error, we found here's our common factors that cancel. Okay, does this x and this x cancel? So if I work to simplify this into x minus 1 over 5x plus 3, can I cancel x's? Okay. The most common mistake from students is to think that you can cancel individual terms from factors. You can't. You can only cancel things, entire groups of things that are being multiplied. And that's the only thing you can cancel. So you can't cancel the x's because they're being added and subtracted. So here's your simplified fraction. You do need to identify any domain restrictions that are not apparent in the simplified form. And so go back and look. Were there any factors in the denominator that were canceled out? Yes. What restriction or what domain restriction was necessary for that factor? Here we see x could not be +3 divided by 5, so x not equal to 3/5. Is that apparent in the answer itself? No. So you have to identify it as a specific domain restriction. Okay, and so this would be your completed answer form. Okay. All right, if you haven't finished the other two, go ahead and just take a couple minutes and try those. If you are finished with them, you can begin on the homework for the 4.1. Because we'll get started on that as soon as I go through these two examples. All right, let's take a look at the second one. Okay, once again, we have this difference of squares. However, this is one of those special forms where we have a binomial squared minus another base squared. And it's still going to fit that pattern. And the pattern is, when you factor it out, you're going to take the sum of the terms being squared times the difference of those. So here's our a value. And here's our b value. So if we take x plus h as our first term, use the whole binomial, and our second term is x, and then just take the sum of those times their difference, and we're going to divide that whole thing by h. So as I simplify this, I have x plus x gives me 2x plus h. And here, x minus x, those cancel, leaving just the h. And you can now see the common factor of h will cancel out, saying 2x plus h is our final answer. Okay, now, did I cancel any factors from the denominator? Yes, so I have to account for that domain restriction, the one that got canceled out. So what can h not be? 0. Is that apparent in the form of this answer? No, so we need to exclude that with a domain restriction. All right, let's go to this last example. Okay, so here we have a numerator that is the difference of cubes. Okay, so the special pattern for difference of cubes, and I'm just going to, I guess I can fit it in here. Okay, we're going to have a binomial times a trinomial. That's our factor pattern for difference of cubes. So first we're going to take the sum of the terms being cubed. We have x and we have a negative a. Remember, the sign can carry with that second term. So those are the two terms that are being cubed. Our trinomial factor is going to be the first term squared. The last term of our trinomial is going to be the second term squared. So negative a quantity squared is plus a squared. And then our middle term is going to be the opposite of the product of these terms. So x times a negative a is negative ax. Change the sign, we get plus ax. So there's our factor pattern for the difference of cubes. And now we're going to divide it by. What do you notice about this factor in the denominator? Is it written in the form that we've identified as the standard form for those? Is the x written first, bless you, with a leading coefficient that's positive? No. So in order to write the x first and make its leading coefficient to be positive, what would we have to do to each of those terms? Factor out a negative. So if we take out a negative, this a becomes a negative a, and this negative x becomes a positive x. I'm reordering these into that standard form. And now we can look to cancel. The x minus a's cancel. So you're left with, and anytime you have a negative 1, you can either leave it as factors, so you could write your answer in this form, or you could distribute your negative through, and you get negative x squared minus ax minus a squared. I don't care. Either of these forms is fine. If it's asking you to write it each as polynomials, you'll use this bottom form. But for the most part, when you reduce your fractions, you can usually leave them as factors. Okay, so even if the denominator stays with multiple factors, just leave them in the factored form. You don't have to combine them or expand them in this particular type of problem. Okay, so did we cancel a factor from our denominator? Yes. So in looking at the domain restriction here, x cannot be a. So is that shown in this final form? No. So we have to identify x not equal to a. Okay, so whichever form you choose, again, it doesn't matter. They're both correct. But you do have to put that domain restriction in that. All right. So again, here's how it differs from what you guys, in the past, you guys only labeled the domain restriction if it was shown in the answer, right? If it got canceled throughout it, you never identified it. Now it's just the opposite. If it's apparent from the form of your answer, leave it. You don't have to do anything. If it gets canceled and disappears through the process of simplifying, you have to account for it and include it.